Question number 5. Explain the convention used to determine the sign of the potential difference around a single loop in Kirchhoff's second rule. Around a single loop circuit containing several resistors and sources of EMF, given the assumed direction of current and the direction of analysis. Analyze single loop circuit containing two sources of EMF and circuit elements as a figure 6.5. This about Kirchhoff's loop rule, conservation of energy. Kirchhoff's loop rule said that the potential difference around a complete circuit loop must sum to zero. What it mean? It means all potential electromotive force plus potential drop, it must equal to zero. The algebraic sum of the potential difference in the loop closed circuit equal to zero. What is a loop? Loop is a group of electrical component and wire that form a closed path like this one. You can go through any loop clockwise or counterclockwise. Look to this figure. This figure we can determine, we can write three loops. Blue one, red one, and green one. In loop 1, blue one, we have two resistors and we have two batteries. What about red one? We have two resistors and one battery only in this loop. And the green one, outside loop, we have two resistors and one battery, it's V1. In this table, we can use this table to know the sign of potential difference for each element in the circuit. Table 6.1, convention used to determine the sign of potential changes around a single loop circuit containing several resistors and sources of EMF. If we have a resistor like this resistor R, and the current flow in this resistor from left to the right side, a positive terminal in this side, negative terminal in this side. If we move in the same direction of the current clockwise, if we move in this loop clockwise, potential difference in this case equal negative. The negative sign, we found it after we get out from this element. Negative what? Negative I multiply R. Because I is the current, multiply R, it's equal potential drop. But we have resistor like this, and the current also flow from left to side, positive and the negative sign. We move in this direction anti-clockwise. After I get out, I found the positive. Positive what? Positive IR. It refers to potential difference across this element. What about battery? In battery, there is a difference. Battery, the long side is positive, the small side is negative. If I move in the same direction of the battery, like this, delta V in this case equal positive VEMF for this battery. This battery, it has VMF. But if we have a battery, the long one is positive, small one is negative, and it has VMF, electromotive force, and we move in opposite direction like this, we will find the negative V EMF. It's referred to delta V for this battery. Look to the table again. We have two elements, resistance or resistor and battery, R. Direction of analysis. If I move in the same as a current, I move in the same direction as a current, like this figure I show you. If I move in the same direction of current, potential change will be negative IR. The element is R, opposite to the current. If I move opposite to the current like this one, potential change, it will be positive IR. What about battery? In the same as EMF, this direction same as VEMF. We will find positive positive. VMF, opposite direction of EMF, like this one. Opposite direction will find negative VMF. Again, the current flow down, positive up, negative down. It's negative. I found the negative after I get out in this direction, negative IR. The current flow up, positive down, negative up. I move in this direction, I found the positive IR, positive. I move in this direction, I found the positive VMF. I move in this direction, negative VMF. All of this Kirchhoff's second rule. Look to this figure. We have two batteries, two resistors. We need to write an equation for this closed loop. How many elements we have? We have 4 elements. I start from this point, move clockwise as you see. This side is positive, negative because the current moves in this direction. The long one is positive, the small one is negative, and the current make this side is positive and this is negative. I get out from this element, I found negative. Negative what? Negative IR2. Then I move out of the battery negative also, negative VEMF2. Move out of this battery positive, positive V1. Move out of this element negative IR1, it's equal to 0. Now I wrote what? An equation for this loop. The same figure, but we change the path direction, anti-clockwise or counterclockwise. There is a positive, negative, and the battery we know which sign is positive and which sign is negative. I start from this point and move in this direction. First, I found the positive. Positive what? IR1. Positive IR1. Continuous moving negative. Negative what? V1. Then out of this battery positive V2. Continuous positive IR2. It's equal to what? Equal to 0. The both equations are the same, even we change the direction of analysis. First question. In the loop shown in the figure, if we start from point A, I start from this point, the current move in this direction. When the current flow in this resistance make positive and the negative, as you see. If the current move in this resistor, make positive side in this and the negative side. I start from A and move in clockwise direction, which equation express the sum of voltage through the loop. Out of this element negative, I multiply R1. Out of this element positive, V1. Then negative, I also multiply R2. Negative V2 equal to 0. This is an equation. We can select the correct choice. Question number 2. When analyzing loop in electric circuit, which of the following assumption is correct for the conventions used to determine the sign potential changes? Resistance, same as a current, as you see, resistance, current in this direction, positive, negative, in the same direction, negative IR, it's correct. Resistance, current, positive, negative, opposite to current, opposite, positive IR, it's correct. VMF, same as EMF. Now, same as EMF, I found the positive VMF. VMF, opposite, negative VMF. So that this table, all of this table is correct, as you see. Other table, not correct. Point number 6. Define the electromotive force EMF as a potential difference. Electromotive force, not a force. It's a potential difference supplied by the battery or device, EMF device. Figure 5.10, simple circuit. There is a battery and a resistance. Battery, it's VMF, it give voltage to the circuit, resistance, it consume voltage from the circuit. If I put voltmeter in this side, will read electromotive force. If I put voltmeter in this side, will read potential drop. Number 7, identify that at least one component in the circuit must be a source of EMF. Like battery is a source of EMF, like generator is a source of EMF. So that to derive current through the circuit, if we have a circuit without battery, there is no current will flow through this circuit. Battery, it's push current through the circuit. Number 1, the electromotive force EMF is electric force? No. Electric force? No. Electric field? No. VMF, it's electric potential difference or voltage. Which is correct about the battery? Battery supply the circuit with a constant current? It's not correct. Because if I have battery like this, 9 voltage and resistance is 3 ohm. What is the current in this case? I equal V over R equal 9 over 3. It's equal 3 amp. If I take the same battery and connect it to another resistor with 9 ohm, 9 voltage connected to 9 ohm, I equal V over R equal 9 over 9 equal 1 amp. The battery supply the circuit with a constant current. It's wrong. Supply the circuit with a constant EMF. Yes, it's correct. EMF not changing. If we change the resistor, the battery remain constant. Number 8, define the mAh, milliampere hour, as a unit of charge, where 1 milliampere hour equals 3.6 coulomb. Milliampere hour is a unit of charge measured in coulomb, and milliampere hour, if we need to convert from milliampere hour to coulomb, multiply 3.6. A typical rechargeable AA battery is rated as 700 milliampere hour. It means charge equal 700 times 3.6 to convert it to coulomb. It's equal 700 times 3.6, 2520 coulomb. How long? He asked about time. Can this battery provide a current of, current is I, micro multiply 10 to the negative 6. Q, it's equal I times T, then T equal Q over I. Q is 2520, I 100 multiply 10 to the negative 6. We use the calculator. Answer over 100 into 10 negative 6, 25.2 times 10 power 6 second. It's a time. If I need to convert it to hour, we will divide by 3600. Divide 3600. It's equal 7000 hour. Number 9, apply the equation R equal rho LA. Rho is resistivity, L is length, A is area. In solving a problem to calculate an unknown quantity given the other quantities. Example 5.2 in page number 123. In this example, resistance of a copper wire. Standard wires that electrician put into residential housing have fairly low resistance. What is the resistance of 100 meter? 100 meter is length. Standard 12 gauge. There is a table in the book. This number refers to area in millimeter and diameter in millimeter also. So that this number 12 gauge copper wire has a diameter of 2.053 millimeter from the table, and its cross-sectional area is then this number. Millimeter, it means times 10 to the negative 3 square equal 10 to the negative 6. Why? Convert from millimeter square to meter square. I need area and length. 12 gauge. Copper wire that is typically used in wiring household electrical outlet. He asked about what? What is the resistance? Resistance is R. R equal rho resistivity, L length over area. Resistivity for a copper is this number, 1.72 into 10 power negative 8. Length is 100, divide area 3.31 into 10 negative 6 using your calculator. 1.72 into 10 negative 8 times 100 over 3.31 into 10 negative 6, 0.52 ohm. A copper wire of a length L 250 meter is needed to provide a resistance of, it's R. What is the radius or small in meter? We can convert it to millimeter or anything. The wire suitable for this mission, copper resistivity, it's rho. The same equation, R equal rho L over what? Over area. Area is by R square. R is 1.5, rho 1.72 into 10 negative 8, L 250 over pi times unknown square. You can use shift solve like this. 1.5 alpha equal fraction 1.72 into 10 negative 8 times 250 over shift pi times unknown alpha x square. Shift solve equal x is 9.5 into 10 negative what? Negative 4 meter. How to convert from meter to millimeter? I know from millimeter to meter times 10 to the negative 3. If I need to convert from meter to millimeter, divide 10 to the negative 3. The answer, divide 10 to the negative 3. Why? Answer. It's equal, what is this? We can write it. 9.5 into 10 negative 4 over 1 times 10 to the negative 3, 0.95 or 0.96 millimeter, because we rounded this number. Question number 2. A potential difference of 12 volt delta V is applied across a conductor 0.5 S conductance. Conductance, it's G, capital G. Conductance equal 1 over resistance. So that the first step, resistance equal 1 over conductance equal 1 over 0.5. It's equal to ohm. S is Siemens. How much current? Current is I. Measured in what? Measured in ampere. Will flow through the conductor. I equal delta V over R. 12 over 2. It's 6 ampere. 100 volt per meter, it's electric field. Electric field is applied between the terminal of the conductor by a battery. A current with this number density, it's J, flow through the conductor. What is conductivity? Conductivity is sigma. Conductivity equal 1 over resistivity. And also resistivity equal 1 over conductivity. Conductivity measured by ohm meter to the power negative 1. There is an equation rho equal E over J. Rho I can substitute it by 1 over sigma. 1 over sigma equal E over J. So that sigma equal J over E. J density 7.4 into 10 power 9. E 120. The answer is 7.4 to 10 power 9 over 120 6.17 times 10 power 7, or 6.2 times 10 power 7 as it's written in what? In multiple choice, after rounding the number. Question 4. A copper wire is intended to be used to provide a resistance. It's R. If you know that the radius of the wire is millimeter, multiply 10 to the negative 3. What length, L unknown, should the wire be? And we have resistivity, it's rho. R equal rho L over area by R square. We can substitute R is 2 equal 1.72 into 10 negative 8 multiply unknown over pi multiply 0.1 times 10 to the negative 3 squared. Shift solve. 2 alpha equal fraction 1.72 into 10 negative 8 times unknown, divide shift by multiply 0.1 into 10 negative 3 squared, shift solve equal 3.65. L equal 3.65 or 3.7 meter. Number 10. Identify that same current flow through a set of resistors connected in series. In series connection, the same current flow in each resistor. I1 equal I2 equal I3. Due to the fact that electric charge is conserved, the charge enter the circuit from one side, it must equal the charge out of the another side. Calculate the equivalent resistance for resistor connected in series. Equivalent resistance Req, it's equal R1 plus R2 plus R3, or we can consider it Req equal N multiply R in case of the resistance is identical or identical. Equivalent resistance is greater than greatest one. Question 1. Two resistors A and B are connected in series. Resistor A have a very large resistance and a resistor B has a very small resistance. The equivalent resistance of this combination will be greater than greatest one, greater than A, greater than resistance of the resistor A because it's greater than greatest one. Number 2. A nichrome wire with a length is L, and 1 millimeter radius times 10 to the negative 3 is connected to 12 volt battery delta V as shown in the figure. What is the ammeter reading? He asked about current measured in ampere. The resistivity is rho 108 times 10 to the negative 8 ohm meter. First step, R equal rho L over area by R square, rho 108 into 10 negative 8, L 1.2 divided by pi times 1 into 10 negative 3 squared using a calculator. 108 times 10 negative 8 times 1.2 over shift by times 1 into 10 negative 3 squared, only this is squared, okay, 0.413 ohm. What about current? I equal delta V over R, 12 over answer, it's equal 12 divide answer, 29.1 ampere or 29 after rounding the number. Number 3. When 125 voltage delta V EMF is placed across two resistors in series, the current is 5 amp is present in each of the resistors. When the same EMF 125 voltage is placed across the same two resistors in parallel, one time in series, another time in parallel, the current through the EMF is 25 amp. It's I total. What is the resistance of the smallest resistor. In case of series connection, we have two resistors, Req, it's equal R1 plus R2. Yes. And Req equal delta V over I total equal 120 over 5, it's equal 25. It means 25 ohms equal R1 plus R2. Then R1 we can consider it 25 minus R2. We have one equation from series connection, and in this equation we have two unknown. What about parallel connection? Req in parallel equal R1 times R2 over R1 plus R2. Yes, and also we can consider Req equal delta V over I total. 125 over 25, it's equal 5 ohms. So that 5 ohms equal R1 multiply R2 over R1 plus R2. The second equation with the same two unknown R1 and R2. We can substitute R1 from first equation in the second equation. We can write it like that. 5, it's equal, I substitute R1. 25 minus R2 multiply R2 over 25 minus R2 plus R2. R2 deleted with R2. Cross multiplication and rearrange the equation. 5 times 25 equal 125. 25 times R2, it's equal 25 R2 minus R2 times R2, R2 square. Rearrange the equation. On the other side, R2 squared minus 25 R2 plus 125, it's equal to 0. Using the calculator, I think mode 5.3. The first one is 1. Enter negative 25. Enter 125. Enter. We have two answers. 18.1. R equal 18.1 ohm. Equal again 6.91. We have two values. We ask about what? Smaller resistance, it's 6.91. What is the smallest resistor? 6.91. The largest one, 18.1. Number 4. 3 different light bulbs are connected in series. 3 different, R1, different about R2, different about R3, with a battery that delivers constant potential difference, VMF. Which light bulb has the highest brightness? Highest brightness, it means highest power. In series, power equal I square R for each resistor. I is constant. It means power direct proportional with resistance. If the resistance increase, the power will increase also. It means the highest resistance has the highest brightness. The bulb with the lowest resistance, the bulb with the highest resistance, yes, correct one. In parallel, the bulb with the lowest resistance has the highest brightness.